All right. So I want to start by explaining how the version of Pilewoki, that we wrote down last time implies a stronger version for instead of counting by Q, counting by degree K eccentrics. So recall that if X is an R to the N, just very briefly, then X K of QT was defined to be the number of points alpha I in X, where each of the alpha i's of degree at most K and of absolute height at most T. We used N, yes.
Matters, right?
Sorry, this was the set, I think. N was the size of the set, right?
Yeah, N was the size of the set.
Yeah, so NK, sorry, X of QT is not what I mean X of KT, and NK of XT was the size of the set. That's right.
Oh, just because you put the size of the X.
Sorry, 1 second. What was my notation last time?
Oh, no, just that you already have equals to the.
Oh, sorry, this is the set.
That's all I meant, that's all I meant.
And this is the size, yes.
Yeah.
Sorry. No. Okay, so let's write down the stronger version of Pilewoki. So we said, suppose X in Rn is reasonable. And take epsilon to be some number bigger than 0. Then there exist finitely many families Wj in Rn cross R to the Mj. Such that for all y in R to the Mj, if you look at the fiber, this is first of all semi-algebraic, and contains an X, so you have finitely many parameterized families of semi-algebraic subvarieties of X. And there is families and sets. Let me say, and for all T, there exist sets Sj in R to the Mj of size at most T to the epsilon, such that all of these points are contained in these fibers. Right? So the exact same statement that we had last time, only instead of just counting rational points, we're counting points in a field of degree at most K. And again, if for example, X does not contain any semi-algebraic curves, then all these Wj's can do is parameterize points, and what this says is you have only T to the epsilon points in a field of degree K. And another bigger conclusion you can draw is if you just remove all the semi-algebraic curves to begin with inside X, all that's left is T to the epsilon points in a field of degree at most K and of height at most T. Okay. So what I want to do is I want to explain how the previous version wrote down, where this was, so proof, let me call this like a, so proof of reduction, let me say. From xkt to xqt, or I guess x1t. Okay? So I want to explain how if we can just count rational points, we automatically, for the stronger statement, we get the upgrade to degree k points. Okay, so what we do is the following thing. We first note that if the degree of alpha is less than k, less than or equal to k, and the height of alpha is most t, that means that alpha satisfies some polynomial whose coefficients are rational numbers, whose height isn't too big. Then there exists a0 through ak, q. This is the height of alpha. Sorry. With height at most some constant times t to the k, such that the sum of ai alpha to the I equals 0. Okay? So basically, if the degree is exactly k, you just take the minimal polynomial. If the degree is less than k, take the minimal polynomial and just multiply it by x as many times as you get it. Okay, so what we do is we define x prime in r to the n cross in r to the n cross r to the, how should I write this? Let me write it as r to the k plus 1 to the n. So in total you have kn plus 2n. Or you do the following. So you have your alpha, which is an r to the n. Sorry, alpha 1 through alpha n. And then for each one of these, you record a I sub j, where I is between 1 and n, j is between 0 and k, and the condition is, first of all, you want the point alpha 1 through alpha n to be inside x. Okay, so this is a natural bundle over x, or manifold over x. And now these aij should record some sort of relation for the powers of the alpha I. So the sum, write this correctly, j equals 0 to k of aij alpha I to the j is equal to 0. Okay? Now note that by the observation, so by, let's call this whole thing star, this fact. So by star, if I look at x prime of 1 comma t to the power of k, let me just say k plus 1 to avoid dealing with these constants. And if I project this onto R to the n, this contains x of kt. In other words, every point in x in the field of degree at most k of height at most t lifts up to sorry. No, I messed up 2 levels. Sorry, 1 second. Sorry, it's not a, sorry, it isn't quite true because the points here are still not defined over the rational numbers. It's still not quite true. I'm sorry. Something very similar is true. Sorry, I roughed a tiny bit. So I'm going to make one more definition. So let x double prime be the projection to rk plus 1 to the n of x prime, which is inside r to the k plus 1 tangent, or to the n, yeah, which is inside r to the k plus 1 n. Sorry, so now keep track of only the coefficients of the point. Okay, and now what's true is if we look at x of kt, is if we look at the x double prime of qt, t to the power of k plus 1, and we pull it back to x prime, and then we push this forward down to x, then this contains x of kt. Sorry, this is what I meant. Right, so the point is we're recording these alpha i's just by recording some polynomial that they satisfy, which is like a legitimate way to record these guys. And the point is, yeah, what is this saying? This is saying, well, if you look at any point here, so any point in x of degree at most k of height at most t, that's saying you can lift it to a point here where the coefficients are rational and their sizes are at most t to the k plus 1. And then you can project it and see it down the next level prime. Okay. Questions about this? The idea is very simple, but seeing it down is a bit tricky. Okay, so now you fix epsilon bigger than 0, and by Pillow-Wilkie for the case k equals 1, there are families Wj inside r to the k plus 1 and cross r to the mj, with wjy being an x double prime and algebraic, semi-algebraic. And sets S sub j in RDMJ with sizes 1 to the power by t to the epsilon. So here we have t to the k plus 1 instead of t, just by shrinking epsilon by k plus 1, you get a t to the epsilon over here. Give a definition of x prime on the board for a second longer. With x double prime of 1 t to the k plus 1, side the union over j, the union over sj of wjy. Okay. Okay, so now the whole idea is to just take these families and we pull them back. Okay? So now define sort of W naught J inside R to the n cross R to the mj by W naught J is you take Wj you pull it back to x prime, and note that the map from x prime to R to the k plus 1n, this is an algebraic map. All it does is takes the coefficients and adjoins the root. So if Wj was algebraic, so it would pull back. And now we push this forward to R to the n. And again, if it is semi-algebraic, so is the push forward, as we'll discuss in a little bit more detail later. Okay, and that's the end of the proof. Then you have these new families W naught J, and X of KT is contained inside their fibers over the same S of J's. Questions about the proof? So yes, I want to point out that even if you only cared about curves in R2, what this actually does is you start from a curve in R squared and you're interested in this point's degree at most k, and you end up with sort of a high dimensional variety, a codimensional 2 variety inside 2k plus 2 dimensional space, k plus 1 times 2, and then you count rational points there. And so even if you only cared about curves, but you cared about arbitrary degree points, like we do for the modular curve case, say, for Andreort, you still feel high dimensional varieties. The other thing I want to point out is in order to get this reduction to work, we really need the stronger statement with these families Wj. Because if you look at this, if you look at x double prime is going to equal x double prime out. Because the way it's defined is incredibly algebraic. So look at a point and look at all polynomials that point satisfies. And that's going to be an algebraic, or in fact a linear variety. So x algebraic is x double prime is fibered by positive dimensional linear spaces. Okay, so as a result, if we only had written down the statement, which is true, but if we only wrote down the statement that if you remove the algebraic guys, you get t to the epsilon, this would not be, we couldn't prove such a reduction. The stronger statement is really important. Okay.
So you think everything depends on k, right?
Yes. All the family constants you mean and stuff? Mm-hmm. Yes, everything depends on k very strongly. Yeah, there's no, even as far as I know, not even an attempt to make things uniformly dependent on K, or even explicitly. So there's sort of this Kilowoogie, the proof is supposed to be, in theory, it's effective. You can write down effective stuff for it. No one's actually written it down. I feel like it always gets asked by many people, including Sarnak, if you can make it self-effective, and he usually says probably, but it hasn't actually been checked yet. All right, so what I want to do is, before, I still haven't told you guys what reasonable means, and I might do that by the end of this class, especially at the beginning of the next one. But for now, keeping the definition of reasonable hidden in a box, I want to give you the idea of the proof of this fact, just so we sort of don't change tracks so quickly. Okay, so the other proof actually follows, for curves in R squared, we gave sort of two proofs, one in more detail. The first was just a Taylor series computation, and the second proof, we actually proved some cool stuff with functions. So in fact, the proof follows the Taylor series computation more. So what you do is the following. You say, suppose that, how should I write this? Let me write. So let me start with the lemma, which I'm not going to prove, but I will state. So suppose f from the interval to k to Rn is a C let's say m function extending to a neighborhood of the interval okay. So we don't want any nonsense at the endpoints, so we sort of assume it extends a little bit further than it does. And we care about rational points on the image of f. Okay? Okay, so now, okay. And fix some positive integer d bigger than 0. So then if m is large enough in terms of k, n, and d, gives us saying that for every k, n, and d, there's large enough m. Then the image of f, if you count rational points of height at most t, is contained in at most t, well, big O, of t, so the sum function defining of k, n, and d hypersurfaces. So right is codimension 1 of degree d. With this function, r of, how do they write it? K, n, and d, tending to 0 as d tends to infinity. So let's unpack this a bit before we go into the proof, which we're not really going to go into. So assume for a second that k is 1 and n is 2. Then what is it saying? It's saying we have some curve in R squared, and suppose that it's sufficiently differentiable. Okay? And then it's saying that if we fix some large d, we can make all the rational points of this curve be inside very few curves of degree d inside R squared. So if you think about it that way, for that case, k equals 1, n equals 2, this is exactly what we proved with the determinism method. Alright? So this is like a direct generalization, essentially. That method stated a bit differently with this parameterization, which ends up being like a nicer way to state things.
So what do you mean by image of f qt?
So I'm saying look at the image of f, and then count. So it's the image of f qt. Yeah, sorry. Mm-hmm. Yeah, so it's really a statement about something inside RDN. This is sort of a nicer way to record it. Other questions? Okay. So the proof is exactly the same as before. Almost identical. So what we do, so sketch. What we do is the following, is we break up, let me just record what I is. So I is 0, 1, 3. So the first step is you break up I into, let me call it m to the k cubes of side length 1 over m. Okay. Okay, now if you have point x, let me say x, if x1 through xk and x not 1 through x not k are points in ik, so break up ik into these cubes. If these are points in ik lying in the same cube, what we do is we can Taylor expand f of this point as being very close to this point. We can write f of x1 through xk as the sum over monomials v of degree at most m of the vth derivative of f at the central point divided by what I'm going to call v factorial, just the product of the factorial of the coefficients of v, times the power of vj plus big O of 1 over epsilon to the m plus 1. So 1 over n to the m plus 1. Okay. Okay, so pictorially we have I, we break it up into a bunch of cubes, and within each cube we Taylor expand f around some central point that we pick. And the higher m is, the better we can do this before all we're left with is just some error, 1 over to the m plus 1.
So before you erase that,
Sure,
so
sorry.
this particular lemma, if I replace q by like degree less than k,
Yeah.
degree less than something, like what do I need to modify?
Can you repeat it? You replace q.
So in this particular lemma, if I just
Oh.
do I just have to?
That's a good question.
With the surfaces, like the degrees just go up.
You're saying if you make this function something else, and this constant something else, you have the same lemma for xkt. It's a good question. I believe that the answer is yes. That this lemma you can pull back in the same way formally. So yeah, I think the answer is yes. You just record the same sort of variety for the for f here. And you compose, you get hypersurfaces there, you pull back and push down, that should be the same. You gotta keep track of how degrees increase when you do the pull back and push forward operation. But yeah, I think the answer is
So that r might be k like much slower, right?
yes, so I mean two things might happen, right? First of all, r is going to decay slower, and second of all, you're going to need m to be bigger, because all your operations are going to make your functions a little bit less differentiable. Even though things are algebraic, you're going to have things like root x appearing. So root x isn't so differentiable with 0. So even like algebraic functions can be a little off. So you have to worry about that. But yeah, I think the limit is to be true. I mean, the reduction I gave was so robust that you can actually take the proof here and carry it over to a proof in that case. Yeah, okay.
How fast is R decay to 0?
Yeah, they had something in their paper. Like, so we had our R be like t to the, in our case, with 1 and 2, it was like 1 over d, right?
Okay, right.
Is what we had. I think it's smaller, it's slower here, but I don't remember. Yeah. I didn't actually check this part very carefully. It's just sort of combinatorics, again, right now, no one doesn't add it up. So, I mean, the idea is the following. So the idea is now what you do is you look at you go from f from I to the k to r to the power of monomials of degree less than or equal to d, where you literally compose f. So this is like, let me call this like f tilde, where this map is literally apply f here to Rn, and then f maps here by taking every point and writing every single monomial of degree at most here. The same thing with its recurs. And now what you do is you say that if you have a bunch of points, so let's call this number like L, you have a bunch of points in I to the k in the same cube of here. Then what you do is you compute the determinant, so let A be the determinant of these images. And now we're going to get, again, arithmetic lower bound and a geometric upper bound. Okay, so on the one hand, A is at least, so, sorry, they're part of the same cube, and you assume that f of these guys is in this set. Okay, so we're now looking at how many points have images that are rational with bounded height. Okay, so on the one hand, if you look at this determinant, well, these guys have bound denominator. So if A is not 0, you can show that this is at least 1 over t to the power of some power. And what power actually? Well, is the sum of all the monomials of degree d. The sum of the degrees of all these monomials. So you can actually write dl over here. Degree most d, there's L of them, so you get up to a constant. This kind of lower bound. This is arithmetic over here. And what's the upper bound? Well, the upper bound is you just Taylor expand, right? And so you're in a linear space spanned by these kind of guys up to very small error. And so you can write down what the determinant actually is. At most, sort of the determinant of a bunch of these different monomials. So it's at most, you can get, so let's see, you can get like 1 over m to the something times t to the something. Again, you have to work it out. Yeah, coming from here. And so if m is large enough, you get a contradiction. Okay? So yeah, I don't really combinatorics, but you just do the same proof as we had before. And so if m is large enough in terms of t, you get a contradiction, and the question becomes how small can you take m? So the smaller m is the sort of better result you get, because they're all in these cubes. Right, so then if a is forced to be 0, what does that mean? It means that this determinant is always 0, which means these monomials always have a linear relation among them, which exactly means you're inside a hypersurface of degree of most. If determinant A equals 0 for all points xl in the cube C, then in a cube C such that f of x5 is in the image of f qt, and that means that all these points lie in a curve, a hypersurface of degree d. Okay, so that's the lemma. Note that we're not saying anything about whether these hypersurfaces lie inside X or just intersect X infinitely many points, or in a variety or something like that. All we know is that these points lie inside some hypersurface of degree d. Okay. Now let's get back to the proof of Bilow-Wilkin. And what we do is we go by induction on the dimension of x. Okay? So step 1 is is we reduce to the case where x is inside the interval to the end. So how do we do this? X a priori is inside all of R to the n. But the point is, the idea is that if we look at the map, x goes to 1 over x, this preserves height. Right? So what we do is we break up x into 2 to the n pieces. Well, I guess let's say 4 to the n pieces, depending on if a coordinate xi is in minus infinity minus 1, minus 1, 1, or 1 infinity. So break up to a bunch of regions. And then for each region, we apply this transformation to all the coordinates which are bigger than 1 to get them to be something less than 1. Okay, so we're literally cutting x up to sort of compact like pieces, inverting it. So for this to be reasonable, we need to know that like reasonable sets x, you can do this to and get reasonable sets x. We haven't talked about it all. But assuming that's good, we can do all this.
Oh, sorry, just before you erase that. Sorry. The map from R to the n to the monomial, you just compute like all the monomials, I guess?
That's right.
Okay.
Yeah, it's like a Segre embedding.
Okay, yeah, sure.
Mm-hmm.
That's it.
Okay. Okay. Okay, so step 2 is parameterize x with finitely many Cm functions f from I to the k to R to the n. So break it up into regions and parameterize each piece. Again, so this, sure you can do this is a big part of this whole reasonable discussion, but we can do this kind of thing. Okay, so now step 3 is find D such that R of nkd is less, well, actually it's strictly less than epsilon. That's an epsilon to begin with. So find D since we're inside T with something less than epsilon, many hypersurfaces of degree D. Okay? So then you can write X as a union over some set S of X intersect, so of Y in S, WY, where WY is a hypersurface of degree at most D. Sorry, we can write X of QT is inside here. I mean, all the rational points are had at most T. I contain sets of hypersurface degree D, so like write down what hypersurface is. Okay, so now the point is we do two things. So one, now if X is inside WY for some Y, then we can go by induction on N. Because any algebraic variety is essentially R to the N after reparameterization. Some Y. By induction on N. So then we start the argument again, sort of inside WY, the same way we did before. If not, So if not, the dimension of each of these guys is less than the dimension of x. Which means by reduction that we already know that all of these points can be parameterized by finitely many families, same algebraic families, with very few points in each family. Okay? So we know that the x intersect wy can be contains finitely many semi-algebraic families containing sort of most rational points. By induction. Okay, so now we can't simply conclude from here because each x intersect wy is a different variety, which we have to start the whole thing over again. But the point is, if we could do this uniformly, then if we could prove the theorem sort of simultaneously for x intersect wy for all y at the same time in a compatible way, then we'd be done. Okay? So if we can do this uniformly, then we're done. Okay, and so that's all the time. Okay, but so that's the point. So in fact, what you end up doing is you can't prove this uniformly. You parameterize these guys entirely uniformly. And it's sort of believable here, because all we're doing is intersecting with families of hypersurfaces. It's a very nice, compact sort of family. We reparameterize these guys all at once. We do it together, computation of x, and you sort of finish by induction. So the sort of, in fact, what I wrote down wasn't actually the full statement of Peter-Wilkie. Let me finish by sort of running a surprise theorem. So uniform Peter-Wilkie. This is what they actually prove. What you do, you don't start with x, but you start with x inside Rn cross some Rs. Where you think of this as a family of x's, for which you want to prove the Peter-Wilkie we wrote down all at once. Okay, suppose this, an epsilon bigger than 0, then there exists finitely many W in Wj in Rn cross Rs cross Rj such that W sub yz is inside, so W sub y is inside x, and so this is the y space, this is the z space, and W sub yz is semi-algebraic. Such that the counting theorem is true. So, such that for all y, x of q, xy of qt, for all z, xz of qt is in at most t to the epsilon fibers of wj. Wj sub yz. Okay, so basically we do the whole thing uniformly over an RDS. And so if you start with things being set up in this way at the beginning, then this step fits naturally into the induction. Okay? So this is the theorem you actually find in inside their paper. All right. Questions?
When did this result come out?
I believe so. One-buried Pila came out in '88, and then Pila wrote a paper on surfaces in '95, maybe. And then the work of Pila and Wilkie, I believe this paper came out in 2006. And then Pila wrote a follow-up paper on algebraic points, maybe like a year later or something. Yeah. His website is very readable, so he has all these things laid out. Okay, so let's stop here, and the next time we'll actually talk about homonomiality, about these concepts.